Hi everyone, welcome to the next session on low power VLSI design. So in previous session we discussed the why we need low power VLSI, that is importance of low power VLSI design, and what are the factors for increasing the power dissipation, and majorly focused on the sources of power dissipation. So first of all, what is the importance of low power VLSI design? So majorly if you're reducing the power consumption of a particular design, the benefits are we can increasing the battery lifetime in portable devices and reduces the cost of cooling effect and packing and lowers the energy consumption. And the different applications of low power VLS is nowadays we are using all the electronic gadgets consuming the low power, that is in mobile phones, laptops, IoT devices, medical electronics, all these things. So the sources of power consumption are dynamic power and static power. So coming to this dynamic power, then the dynamic power definition is whenever the device is in active state and when the signals of the design are changing its values, that is the device is in the operation state. Whenever the device is taking the input value and producing the output, means it is doing some operation. So majorly it is categorized into three types: switching power, short circuit power, and glitching power. Coming to this, first one is the, and the dynamic power is also called as active power, means the device is in the active state. So the first one is the switching power. So switching power means the power required to charge and discharging the output capacitance on a gate. So this is the circuit setup required for switching power, means we are giving the input and what is the output and what is the internal operation of that circuit. So here the switching power is indicating that majorly it is concentrating on the how that working whenever it is accepting the input. So here the power is consumed in CMOS circuits when the transistors are switching its state. That is here the state means from logic 0 and logic 1. And here we connected the load capacitance at the output side. So here consider this is the circuit uh, setup and this is the name of the basic CMOS inverter. So consider this is pull up transistor and this is the pull down. Generally we are using pull up transistor as PMOS and pull down is the NMOS. And if you are applying the input signal, that input signal may be either logic 0 or logic 1. If you are giving the input as logic 0, so for that logic 0, the PMOS is going to the on condition and the NMOS will going to the off state. So here this is in the on state and this is in the off state. So the on state device will form the short circuit and this is the open circuit, open the circuit uh, path. So in this situation, means whenever you are applying the logic 0, the PMOS is in the on state and the capacitor will start charging from VDD to the VDD. To see. So here, this is the path, charging path from VDD to capacitance line, means output side. Suppose if you are giving the input as logic 1, at the situation, the PMOS is going to the half state and NMOS going to the on state, means this is open and this is closed, short circuit path. At the situation, the capacitor will going to the discharge, means it will going, this is non state. So this is in the discharge state. So here, while applying the input signal, the capacitor is charging and discharging. While the input is logic 0, the capacitor is in the charging state. While the input is logic 1, the capacitor is in the discharging state. So the name itself here, the power is dissipated while the capacitor is switching from charging to discharging, discharging to charging. So like that, the energy required for transition is given by half CL VDD square. So VDD is nothing but the supply voltage and CL is the load capacitance. So the switching power is therefore expressed by the expression P switch equal to CL into VDD square into E trans into F clock. Whereas F is nothing but the frequency of transitions and pre trans is the probability of output transition and F clock equals the frequency of the system clock. So finally P switch is equal to the capacitance value into supply voltage into F clock. But coming to this, the switching power dissipation for charging and discharging of the load capacitance. So switching power is also occurs uh, at the internal node capacitance also. So the total switching power dissipation is, this is the power calculated in previous slide, means whenever you are applying that capacitance to that input side and we are getting the output, but the power is also dissipated at the internal nodes also. So this is the power dissipation at the internal nodes. So alpha and Ca is indicating the probability and capacitance of that internal node I. So the total power is nothing but uh, at input side and output side of that circuit and also internal node. So this is the switching power. So switching power is nothing but this is the one major type in the dynamic power. Dynamic power is also called active power. Why? Because this is called active power means in this type the device is in the on state as well as it will do the operation, means it will changing its values, signals are changing its values. So it will be explained by using the basic CMOS inverter diagram. So whenever you are applying the logic 0 to this inverter, the capacitor connected at the load side is going to the charging state. Whenever you are applying the input at logic 1, the capacitor will move to the discharging state. So here the capacitor is switching from charging to discharging, discharging to charging. At that situation, the power will be dissipated. So that will be calculated by using the power formula. So this is the total power formula, including internal nodes also. Okay. Thank you. In next class, we'll see about the another power, that is the short circuit power.